Great. Well, thank you everyone for coming to another Galaxies and Cosmology and Stars and Planets seminar. Today we have two great speakers to talk about different things related to ultra-diffuse galaxies and also magnetic fields in the universe. Our first speaker is Anna Wright. She's a postdoc at Johns Hopkins University. She just started there in September. And are you still in New Jersey or are you in Baltimore now?
I have actually moved. Not that it matters much though.
Yeah. So she's brand new to Baltimore and probably knows her apartment very well. Anna did her PhD at Rutgers University under the guidance of Allison Brooks, and her undergrad degree at Rice University in Houston. And today she's going to talk to us about the formation of isolated ultra-diffuse galaxies in Romulus 25. Thank you.
All right, thanks Anna for that introduction. As Anna said, my name is Anna Wright, and I just started at Johns Hopkins. I work with Molly Peoples, Jason Tomlinson, and the rest of the Foggy team there. But today I'm actually going to tell you about some of the research that I did while I was a graduate student at Rutgers. It was done in collaboration with the N-Body Shop collaboration. The names of my collaborators are listed down here. So I will get started. So I want to start by talking about what ultra-diffuse galaxies, or UDGs, are. These are galaxies that have the luminosities of dwarf mass galaxies, but light profiles that can often extend as far as those of much more massive galaxies. Although similar objects have actually been known about since the 1980s, it's only quite recently that they've been discovered to be a relatively large population. And accordingly, the exact definition of a UDG still varies a little bit depending on who you're talking to. I use the Van Dockum definition, which is to say that I consider a UDG to be any galaxy that has a central surface brightness fainter than 24 magnitudes per arcsecond squared and an effective radius of at least a kiloparsec and a half. If you look at the image on the right here, this is an example of a real-life UDG. This is NGC 1052 DF2. This galaxy looks very low surface brightness. You may not even be able to see it very well on your screen. And it is very low surface brightness, but it's actually on the bright side for a UDG. It has a central surface brightness of 24.4 magnitudes per arcsecond squared. It's also quite extended. Its effective radius, which is roughly the radius within which half of its light is emitted, is 2.2 kiloparsecs. To give you an idea of how this compares to the dwarf galaxy population in general, I've plotted here on the top half of this plot the central surface brightnesses of a population of isolated simulated dwarf galaxies, and on the bottom half of this plot, the effective radii for the same group of galaxies. Anything that is below the solid line on the top half of this plot is low surface brightness enough to be an ultra-diffuse galaxy, and anything that is above the solid line on the bottom half of the plot is large enough to be one. Now, there's nothing terribly special about these cuts. However, they do tend to identify the low surface brightness, high effective radius tail of the dwarf galaxy population. Now, before I get into talking about the particulars of my work on ultra-diffuse galaxies, I wanted to kind of step back and talk about why it's important to study dwarf galaxies and low surface brightness galaxies, and in particular to study low surface brightness dwarf galaxies. Well, perhaps reason number one, I think why it's important for us to study these galaxies is that dwarf and low surface brightness galaxies are the most abundant galaxies in the universe. Historically, we have largely based our understanding of how galaxies form and evolve on high mass, high surface brightness galaxies. But when we look at the number density of galaxies in our universe, we see that these galaxies are really not that common, and it's actually dwarf galaxies that dominate the number density. And we can't really claim to have a complete understanding of galaxy formation and evolution if we can't fully explain the properties of the majority of the galaxy population. Reason number two why it's really important to study these galaxies is that we're about to find a whole lot more of them. Over the next decade, the astronomical community is going to be using instruments like the Vera-Rubin Observatory and the Roman Space Telescope to conduct surveys that will push our current surface brightness limits down by several orders of magnitude. This is going to give us an absolutely unprecedented view of the low surface brightness universe. And while unexpected discoveries are wonderful, and I absolutely can't wait to see what these instruments discover, it's important that we know what we want observations to test. And one way that we can come up with theories to test is through simulations. And this is the method that I use. All of my galaxies come from cosmological simulations. We begin each simulation in the very early universe with, sorry, This freezes about 5% of the time, and you guys are unfortunately in the 5%. Well, in any case, this will continue to expand, and eventually you'll start to see gas. So we begin each simulation of the very early universe with initial conditions based on what we've observed in our own universe, and then we let it evolve according to the laws of physics up until the present day. Cosmological simulations have a lot of advantages when it comes to studying the low surface brightness universe. The primary advantage is that, well, telescopes often have a hard time detecting dwarf and low surface brightness galaxies because of how faint they are. Simulations don't have surface brightness limits, which means that simulators can take a census of the low surface brightness universe without having to worry that we're missing a whole lot of it. There are, of course, also disadvantages here, though, namely in that our galaxies aren't real, and they can only reflect the laws of physics that we know to implement. And this actually gives us another important reason to study dwarf and low surface brightness galaxies. And that's that they provide a unique opportunity to test our models of galaxy formation and evolution, in part because our simulations usually aren't tuned to make them. In instances where we don't fully understand the reason behind a particular property of the universe, or where a process simply lies too far below the limit of our resolution, simulators often have to just kind of do their best to match observations. In most simulations, this is done by picking values for different parameters, like the amount of energy that a supernova is going to inject into the surrounding gas, or the likelihood that a cold, dense clump of gas is going to form a star, picking values for parameters like that best reproduce observed scaling relations. And this means that we're incorporating observational biases into the simulations. These scaling relations are typically primarily based on high mass, high surface brightness galaxies. And while it's taken a lot of effort to create realistic versions of these galaxies in simulations, and I'm sure some people would argue that we're not even there quite yet, this is ultimately what these simulations were designed to do. The real test at this point is whether or not our simulations can accurately reproduce galaxies and properties of galaxies that they weren't tuned to create. If we can make realistic dwarf and low surface brightness galaxies, for instance, and especially if we can make realistic versions of extreme objects like ultra-diffuse galaxies, this is a good indication that our models of galaxy formation and evolution are correct. If not, though, it means that we're missing something fundamental, and there's a good chance it's something that only these galaxies can teach us. Now, for the remainder of this talk, I'm primarily going to focus on kind of the last 2 points here. And that's because thus far, very few ultra-diffuse galaxies have actually been discovered in the field. So I'm going to try to use simulations to compare to the few observations that exist and to make some predictions for what instruments like Roman and Rubin will see when they take deep images of the field. Now, the simulation that I'm going to be using to do this is from the Romulus suite of simulations. These are 2 fully cosmological hydrodynamic simulations. The first is Romulus C, which is a zoom-in of a 10 to the 14 solar mass galaxy cluster. My collaborators and I did actually analyze the UDGs in Romulus C, and we published a paper about it last year led by Michael Tremmel, but I'm not actually going to talk about that at all today. The simulation that I am going to talk about is Romulus 25. That's the simulation that all of today's galaxies come from. This is a 25 megaparsec cube volume that contains thousands of well-resolved galaxies down to low mass dwarfs. Now, the first question that we have to ask is, do ultra-diffuse galaxies exist in isolation in Romulus 25? And if so, what do they look like? Well, we can start with the basic definition that I showed you before. These galaxies will have to have central surface brightnesses fainter than 24 magnitudes per arcsecond squared and effective radii of at least 1 kiloparsec and a half. Additionally, in order to ensure that they're isolated, we require that they're neither satellites of any other galaxy nor within 1 megaparsec and a half of anything Milky Way mass or larger. And when we applied these 2 criteria to the redshift 0 time step of Romulus 25, we found that more than 100 galaxies fit this description, which was a very, very pleasant surprise. And when we started analyzing the ultra-diffuse galaxies that we found in Romulus 25, we found that they looked a lot like pretty typical dwarf galaxies. They have stellar masses less than 5 times 10 to the 8 solar masses. They occupy dwarf mass dark matter halos, here meaning they have virial masses less than 10 to the 11 solar masses. They do tend to have slightly elevated H1 masses for their stellar masses, but they form stars at rates that are quite typical for their mass and environment, which suggests that, like most low surface brightness galaxies, UDGs are not terribly great at turning gas into stars. These results are also broadly what observations of isolated UDGs have indicated. For instance, here I've plotted the H1 masses and effective radii of all of the isolated UDGs in Romulus 25 in red. I've also added all of the isolated dwarf galaxies, here denoted as non-UDGs, in the same stellar mass range in blue. And if I overplot a sample of UDGs that Leisman et al. Identified in alfalfa data, you can see that all the galaxies follow the same trend and largely occupy the same space. In fact, if we limit our analysis to the mass regime where alpha-alpha is considered to be complete, our estimates for the number densities of H1-rich UDGs also match up. Jones et al., who used Leisman's sample, estimated that there are about 0.0015 H1-rich field UDGs per cubic megaparsec. And our estimate, which is based on Romulus 25, is nearly identical. And this is kind of a nice initial sanity check. It suggests that at least at the high mass end, we are producing UDGs in roughly the right number. Looking at this plot, though, you can see that a lot of our UDGs really lie below the detection threshold of alpha-alpha. And this suggests that we should expect future surveys to find quite a few more of them. However, is this prospect even interesting? I've just shown you that UDGs have pretty average properties despite their large sizes and low surface brightnesses. So what exactly is different about them and why? Well, we can get an idea for why UDGs might be interesting targets for future studies and observations by actually looking at the evolution of the properties that we know are different for them. So in this plot, I'm going to show you how the effective radii of all of the galaxies that we identify as UDGs at redshift 0 evolve over time. And for comparison, I'm also going to show you how the effective radii of all of the galaxies that we identify as non-UDGs at redshift 0 evolve. Now, because effective radius is correlated with mass, I've also broken this sample up into 3 different mass bins, just to kind of avoid washing out any differences that may exist at different masses. However, I'm going to start by showing you just the first few billion years of evolution for the highest mass UDGs, which are shown here in red, and non-UDGs, which are shown in blue. The thick line here indicates the median evolutionary track, and the shading indicates the interquartile range. And you can see that for the first several billion years, these two samples are actually indistinguishable. However, they do eventually diverge. Effective radius starts to grow significantly in UDGs, but stays fairly constant in non-UDGs. We see similar behavior in the lower and intermediate mass bands. Another thing worth noting here is that an effective radius of 1.5 kiloparsecs, which I've marked here with a dashed line, is pretty normal for galaxies in the highest mass band here. However, it's considerably rarer in the low and intermediate mass bands. If we look at the evolution of central surface brightness for these same groups of galaxies, we see something very similar. For the first several billion years, UDGs and non-UDGs evolve together, but past a certain point in time, UDGs start to evolve to much lower central surface brightnesses than non-UDGs, which in the highest mass band at least tend to stay pretty steady. We see a little bit more evolution in the non-UDGs in the lower and intermediate mass bands, but UDGs still almost always have the lowest central surface brightnesses. As before, it's also worth noting where these populations fall with respect to the UDG boundary. For our lowest mass galaxies, having a central surface brightness this low is not abnormal, but for our high and intermediate mass samples, it's pretty unusual. If you look especially at the highest mass bin here, there's a difference of 2 orders of magnitude between the median central surface brightness of a non-UDG and the median central surface brightness of a UDG. And we can figure out why UDGs might have particularly low central surface brightnesses by looking at what's happening at their centers. We find that UDGs have less dense gas in their central regions, and this strongly affects their star formation, as we would expect. So here I plotted the evolutionary tracks for the central star formation rates of our UDG and non-UDG samples. And as before, you can see that UDGs and non-UDGs initially evolve together, but the populations eventually diverge, and UDGs evolve to considerably lower central star formation rates than non-UDGs. This is true in all of the mass bands, but it's most significant in the highest mass band, where we just saw that the difference in central surface brightness is largest. Now, as you might expect, lower central star formation rates ultimately lead to fewer stars in the centers of UDGs. And additionally, those stars that they do have in their centers are older and therefore dimmer than those of non-UDGs. The low surface brightness of ultra-diffuse galaxies is therefore a consequence of both lower central stellar densities and fainter central stellar populations. This, however, does not answer the question of what's actually causing the divergence that we see between the evolution of UDG progenitors and that of non-UDG progenitors. If we look at the highest mass bin for each of the plots that I've just shown, we can see that UDGs and non-UDGs start to evolve differently at about the 4 to 5 gigayear mark in the simulation. This is true of effective radius, it's true of central surface brightness, and it's true of central star formation rate. Before this point, we see essentially just a single population, but after it, we have 2 different evolutionary paths. We have the UDG path and the non-UDG path. So what's causing the difference between these? Well, we looked at a lot of different factors that we thought might alter the evolution of galaxies in this way, but it ultimately took making and watching movies of them to convince us that we'd finally found the key factor. So I'm going to show you a movie of kind of the life of one of our UDGs, so you can see what's happening, and then I'll show you something a little bit more quantitative. So this movie shows the evolution of one of our most massive ultra-diffuse galaxies. On the top, we have mock UVI images of the galaxy's stars, and then on the bottom, we have gas surface density. Each of these boxes is 50 kiloparsecs across, and we have a face-on view on the left and a side-on view on the right. So you can see that we start out with a fairly bright galaxy. It does have a couple of kind of initial mergers, but then it stays static for a while. And then we have a 2-to-1 merger that completely transforms this galaxy. This galaxy was always big enough to be an ultra-diffuse galaxy, and the merger obviously makes the galaxy bigger, but it also does something to the central surface brightness. So I'm going to let it play through again, and this time I want you to kind of keep an eye on the center of the galaxy. And what you're going to see is that after the merger, dense gas moves out of the center of the galaxy, and the population of stars that's there fades as star formation dies down. Now we can really see very clearly the effect of this merger on the evolution of this galaxy if we kind of rescale our effective radii and central surface brightness evolution plots with respect to the time of the merger. So here I've placed the merger time at t equals 0 in both of these plots, and what you're seeing for now is just the evolution prior to the merger. And you can see that prior to the merger, the galaxy is actually getting a little bit more compact, and the central surface brightness is pretty steady. Then we have the merger happen, and this gray area indicates the time over which the merger takes place. And you can see that the effective radius starts to grow during that time. And then after the merger, the effective radius continues to grow, and we see a sharp drop off in the central surface brightness. And it isn't just this one galaxy. This is true for nearly all of the isolated ultra-diffuse galaxies in our sample. Here I'm showing the same plot for just the galaxies in the highest mass bin. And you can see that non-UDG progenitors don't really experience very much evolution due to mergers, specifically major mergers. You can see that there is a little bit of an increase in effective radius after a merger, but it's temporary and not very extreme. And although central surface brightness fades over time, there's no specific reaction to the merger. By contrast, UDG progenitors react very strongly to major mergers. We see an increase in effective radius, and we also see a sharp drop-off in central surface brightness. These two populations, non-UDGs and UDGs, are clearly one population before the merger. So it must be something to do with the properties of the merger itself that lead to this divergence. So what is it that's different about the mergers that produce UDGs? Well, initially, it honestly looks like nothing. You may remember that I said it took watching movies of these galaxies to figure out that mergers were the key factor here. And the reason for that is that the merger histories of UDGs look a lot like those of non-UDGs. They have the same number of mergers, both major and minor. They merge with similarly gas-rich things. However, there are two significant differences, and they both have to do with the last major merger that each galaxy experiences. The first is that the mergers that produce UDGs tend to increase the angular momentum of the galaxy quite a bit more than those that produce non-UDGs. And this is probably why we see dense gas moving out of the center of the galaxy being pushed out kind of to larger radii. Now, although UDG progenitors do not form with high spin, and they actually have usually spun down by the end of the simulation, this does follow previous theoretical works that show the high spin can contribute to the formation of low surface brightness galaxies in general and ultra-diffuse galaxies specifically. Now, the second difference between the mergers that produce UDGs and those that produce non-UDGs is that these mergers tend to happen earlier. They almost never start after redshift 1 for UDGs. And one of the big things that this allows for is the fading of the central population of stars in ultra-diffuse galaxies. It means that after star formation dies down, that stellar population at the center has time to evolve to a low surface brightness. And this actually results in kind of an interesting morphology in our UDG galaxies that often distinguishes them from non-UDGs. Central star formation has died down, but we still have star formation happening at a typical rate. It's just at larger radii. And as a result, we have kind of bursts of star formation at large radii It's typically kind of irregular, a little bit asymmetric. Um, and this seems to be consistent with the few images of isolated UDGs that exist. Kind of let this movie play through so I can point it out. So you can see these bursts of star formation along the edges here. This does seem to be consistent with few images of isolated UDGs that exist. However, in order to figure out if this is the dominant method by which UDGs form, we really need more observations. So I'll leave you with kind of a couple of takeaways from this. The first is that we're predicting that future surveys will find a lot of UDGs in the field. Based on our simulations, these will be galaxies that are predominantly H1 bearing and star forming, but which will have lower central gas contents and star formation rates. I'm particularly excited about what Roman is going to see because my current postdoc is mostly focused on making predictions for Roman using the foggy simulations. So I know that's a long way off, but I'm excited about it. The second takeaway is that even if you're a dwarf galaxy living in the field, mergers matter. Even a galaxy that looks isolated at redshift 0 has not necessarily always been so. And we find that isolated UDGs are the products of early major mergers that increase their angular momenta and redistribute their star formation. If you're interested in more details, feel free to look at Wright et al. 2021, which was recently accepted in MinROS. And if you're interested in our results on cluster UDGs, check out Tremel et al. 2020. Thank you for having me.
You were perfect on time. So I'll open it to questions. We have about 5 minutes. So please raise your hand if you have any questions. And I'll call on you. And I'll start. Actually, I have a question. Do you guys look at impact parameters too? Like, do you see how the spin up? So usually the mergers add a lot of angular momentum, causes the stars to spread out. Do you see how that depends on impact parameter that plays a factor?
So we looked at the geometries of the mergers, like the orbits and everything, and we saw no difference between those that produced UDGs and non-UDGs. However, we are working on kind of putting together a halo interaction network that will try to interpolate between time steps so that we can get a better idea of, because there's a chance we're missing things just with the fact that we don't have super close together time steps.
Yeah.
But for the time being, at least, we haven't been able to see anything. And I think part of the reason is that the angular momentum vectors of dwarf galaxies are just not very stable. They have a tendency to completely swing around as soon as a merger starts. And so, was something that you might expect to produce an increase in angular momentum, like an initial kind of lineup between the two galaxies, doesn't seem to matter.
So I guess then the main thing is the timing. So the fact that you have no more mergers after Z of 1. So then it gives the gas time or the stars time to spread out. So it depends on environment most.
So we don't actually see any difference between the environments of UDGs and non-UDGs, at least in a kind of cumulative tidal perturbation sense.
Okay.
But that's something that we're also trying to look into in more detail.
Okay.
Yeah.
Great. Thank you. Angelo?
Hi, Anna.
Hey.
Great talk. I had a question about your plot of H1 mass versus effective radius. It looked like there was this population with really low H1 mass, but then the sizes weren't changing. Do you think that's real or resolution? And what's going on there?
It's hard to say. So these galaxies are, I guess you know this because you work with Romulus. So our H1 masses for a given particle are a percentage. They're based on the density and temperature of each particle. And once we get to that low of mass, it's probably not that many particles that we're looking at. So it's a little bit hard to say if they're real. We are planning to run zoom-in simulations of some of these ultra-diffuse galaxies, which will hopefully tell us a little bit more about what's real. These do tend to be, the ones with really low H1 masses tend to be things that have had some kind of tidal encounter and have had their gas heated a bit, and often they'll have had a little bit of stripping happen. So it could be that the reason that we see their effective radii are still fairly large is because they've actually experienced some tidal heating, essentially.
Okay, thanks.
Razi?
Hi, Anna. That was very excellent talk. So I have a similar question to what other Anna asked you about about how you actually get the UDGs. So I was wondering regarding to the spin, like a spin enhancement because of the merger. Do you have any ideas what really caused that? Like, you can imagine that there are actually these actually galaxies are maybe like changing their spins and actual orientation. So there are different factors like the spin ratio or the alignment between them just before the major merger of the system, and also other things like how much close they get to each other, and also the fact that you have an orbit and then there is apocenter and pericenter, so how much far away they actually get. So if they remain very close to each other, or just like getting very further out from each other, I would imagine that would actually, kind of like boost this kind of spreading actually for back and forth. So do you have any ideas which factor would be more important?
So we did specifically look at alignment between the orbital angular momentum vector of the secondary galaxy and the like spin vector of the primary galaxy. And we didn't see anything there. I tracked it over time for a bunch of different galaxies because I couldn't figure out if, maybe I was just looking at it at the wrong time. And it doesn't appear initially, at least, that there's anything there. But again, we really need more interpolation between type steps to know if that's true. As far as figuring out if it's something with kind of the more specific nature of the orbit once the galaxy has fallen in, like if it's something to do with pericenter, that's again something that we need the interpolation for, just because there's a good chance we'll miss it otherwise.
No, I mean, that's actually true because, in other actual direction, using the cosmological hydro, we're also doing this kind of exploration. But sometimes the time snapshot between actually, the time step between different kind of a snapshot is so long that you can't really easily just interpolate, I mean, it could well be that your orbit, because of the mergers that you have, it's just getting actually kind of like suppressed over the time. And because of that, the apocenter that you see at time 1 is not the apocenter at T2. So they are just like getting, a smaller and a smaller and a smaller. So I don't really know what would be the best way to actually do this kind of interpolation, but good luck with your job, Thank you.
Oh yeah, sure. Thanks for the question.
Sure.
We do.
Go
ahead.
Oh, sorry, go on. No, go on, Anna.
Oh, I was just going to say, so the Halo interaction network we've been looking at building is in collaboration with, this is Kelly Holly Bockelman at Vanderbilt, and it would be based on machine learning, which isn't something that I am at all well-versed in, but I know always that, there are risks there. So, the interpolation may, as you said, it may not work well, we'll see.
So we're short on time, so we'll do one more question. That's just because Alex is constrained with he's teaching a class right after this. So I'm just gonna go in the order. There's plenty of slots in Anna's schedule, so please, if you'd like to chat with her, please add your name to her schedule for this afternoon. So Akos.
Yeah, hi. My question is about the general characteristics of these isolated UDGs. So there's often discussion about the halo masses, that UDGs tend to have very high halo masses. So what are the typical halo masses for these galaxies? Are they overmassive compared to like compared to galaxies with similar stellar mass or not?
So we don't find that they're particularly overmassive. They seem to be fairly typical. So I've pulled up a backup slide on the stellar mass halo mass relation, and the UDGs are marked in red here. We do have a couple that seem to be a little bit overmassive, but these are also, they have pretty low stellar masses, so they're kind of near the edge of our resolution limit. So it's difficult to know how seriously to take those. But we don't, in general, find any serious difference. And I would expect us, if there were, I would trust more finding overmassive ones than finding undermassive ones, in part because we set a very strict resolution limit. And so, if a UDG had too little dark matter, we simply wouldn't even consider looking at it, just because we would consider it to be under-resolved. But as you can see, in general, they follow the stellar mass halo mass relation in our simulations.
Okay, thank you.
Great. Thank you. Thank you. Let's thank Anna again for that excellent talk. And like I said, if you'd like to speak with her, there's still plenty of slots on her schedule. So please check her schedule out. Thank you.
Great. So let's move on to the second talk. Alex, if you can go ahead and share your slides while I introduce you. So our next speaker is Alex Lazarian, who studied in Moscow before doing his PhD in Cambridge, UK. Since 1999, he's been a professor at University of Madison, Wisconsin. And his research interests include MHD, turbulence reconnection, cosmic rays, cosmic dust, also CMB foregrounds, including the effects of dust and turbulence. So he has quite a wide range of expertise here. And today we'll be hearing more about magnetic field in the galaxy and clusters and what implications it has for CMB polarization studies. So without further ado, thank you. And Alex, take it away.
Hello, do you hear me?
Yes, we can hear you.
Okay, wonderful. So, you know, there is a semi-joke among theorists doing astrophysics that if something does not agree between your theory and observations, appeal to magnetic fields. And this sad joke reflects two facts. First of all, it's generally accepted that magnetic fields are extremely important for many astrophysical phenomena. And the second is that we have very little information about magnetic fields, not sufficiently detailed information about magnetic fields. Therefore, I was working on different techniques how to map magnetic fields in new ways or improve old ways. I developed with my student a theory of grain alignment, radiative torque alignment, and also with another student we suggested a completely new technique of atomic alignment, but all of this uses polarimetry. Today we'll be talking about some other technique which does not require any polarimetry and can use available data, available archival data for this new purpose. And to exemplify, I show you this maps of this Planck polarization obtained with Planck satellite polarization, and this is Gulf H1 obtained with just 21 centimeter. And on the right side is the first map of the magnetic fields in the clusters of galaxies. This is cluster M87, and it shows a very rich structure. So this is my group of students working with me, and two of them will be applying in 1.5 years, so don't miss the chance. Last year, Xiao Xu was applying to Harvard, and now she's a Hubble Fellow at the Institute of Advanced Studies, and you missed her, so don't miss the next chance. Key role of magnetic fields is generally accepted well in astrophysical and cosmological communities. Star formation, obvious example. Cosmic ray physics, obvious. It is also known that magnetic fields through polarization from dust and synchrotron interfere with the search for enigmatic beam modes from primordial gravitational waves. But not only that. New frontiers of research require even better knowledge of magnetic fields. For example, just one example, the high redshift H1. It is a very challenging problem. The synchrotron foreground is 1,000,000 times stronger than the signal. And in this case, any instrumental polarization plus Faraday rotation of the polarized signal will mess up completely your attempts to measure high redshift H1. You need to know not only two-dimensional magnetic fields, you need to know three-dimensional magnetic fields. Very challenging. Now we live in the golden era of polarization studies. This Sophia Flying Observatory, and there is, for example, this beautiful map of external galaxy made with Hawk Plus balloon experiments, and surely the revolution which was induced by Planck satellite. What are the issues here? It's very expensive, limited coverage, limited sensitivity, and very importantly, we have the integration of the polarization along the line of sight through the whole entire galaxy. So it's very difficult to get any detailed information from that. Therefore, I'm going to discuss an alternative technique. And this is an advertisement of this, just to show you. This is Gulf H1 magnetic fields versus polarization by Planck. And this is VLSC, molecular clouds, 13CO versus polarization of blast pole mission. So this technique is based on MHD turbulence, and therefore let me use this commercial advertisement of the book that my former student Berezniak and me published in 2019, or is Turbulence in Magnetohydrodynamics. The basic properties of the turbulence are used in this technique. So let me, in 2 words, describe these basic properties that we need. Magnetic field can be presented as a, collection of flux tubes. And these flux tubes can mix, be involved in mixing motions. Usually turbulence is presented as a flow of waves along magnetic field lines. But imagine if these motions are possible, they are much more natural and easy. Why they were not considered? Because people were worried. What will happen? The magnetic field lines, we start moving them, they will have these knots, intersections of different magnetic field tubes, and what would happen with them? The theory that Ethan Vishniak and me suggested back in '99 answer this question, and this is they will have turbulent connection, and we will have the disentangling of these knots on the eddy turn over time. Therefore, these eddies are possible, and they are the most natural way of turbulent motions. And this is also an illustration. These are 2 eddies rotating, and as they rotate, magnetic field lines are reconnecting and changing their topology. By the way, this the turbulent idea, the connection idea, were tested in many numerical studies already. So we are using this fact, and the success of this technique also shows that this basic idea is right. If we have a magnetic flux, turbulence would mix up magnetic field perpendicular to the local direction of magnetic field, as it's shown here, and therefore the gradients of velocities will be perpendicular to the local direction of magnetic field. Local is a keyword here. Because of that, we can measure magnetic fields, not only magnetic fields in terms of mean magnetic field, but the detailed magnetic field. How can we explain this availability of detailed structure? It's very easy. Because I told you that magnetic field does not prevent the motions of magnetic field eddies perpendicular to local magnetic field direction. We have a Kolmogorov scaling of velocities. This is L perpendicular, means perpendicular to the local direction of magnetic field. The gradients of velocity amplitudes perpendicular to the magnetic field will be VL over L perpendicular. it scales as L 1/3. So it's the total scaling of gradients is -2/3. So the smallest edges, which are on the available at your resolution limit, will be the most important in terms of tracing magnetic field, and will be most important in your signal. And these edges are exactly going along the detailed magnetic field structure. So these are numerical simulations. They show that indeed these are either contours of velocity, and velocity gradients are perpendicular to the direction of magnetic fields. How can we obtain this through observations? Through observations, we can obtain channel maps. And channel maps in position velocity space correspond to velocity fluctuations. These are numerical simulations, and this is what we show. These are channel map structure, and within this channel map structure, we can find gradients, and they are perpendicular to the local direction of magnetic field. So this is an example of application of the technique for the torus molecular cloud, a famous molecular cloud. This is a Planck image of torus molecular cloud, and this is the image that we obtained with ground-based archival data. And the correspondence of this is given by this alignment measure that you can see. And the particular alignment measure is 074, which corresponds around 4 degrees misalignment between magnetic field and the direction of between the polarization and the direction of gradients. It's also important that we can have something which is not available with polarimetry. We can choose the particular species which are produced at a particular depth. For example, this is the map of Vela C obtained with a CS tracer. And this molecule is formed at the densities more than 10,000 molecules per cubic centimeter. So we are zooming in the gas, zooming into the dense parts of the gas. And here we have the discrepancy between the polarization and gradients around 6 degrees. Well, you should understand that polarization is not measuring exactly this part of the cloud. Polarization is measuring the signal all over the cloud, and also through the diffuse media through the entire galaxy. So we do expect differences. In fact, we can use different measures of different species, and we see which species correspond to better representation of magnetic fields at different densities. This is a combination of a number of species that we get. And in fact, we get a higher alignment measure overall this way. So we can have this 3-dimensional distribution of magnetic fields in molecular clouds. Well, we can also get something which is not available by polarimetry at all. For example, high velocity clouds do not have high column density, and therefore we cannot see them with polarimetry, but we can see them with channel maps. There's a Smith cloud. This is a high velocity famous cloud, and this is the magnetic field structure that we obtained with gradients for this cloud. I already showed this. This is correspondence with H1 polarization obtained with Planck, and the predicted polarization obtained with Galfa maps. We can now get it even better in terms of the correspondence. Moreover, we can do this for higher latitude for which polarization does not have enough sensitivity. This is a comparison with SOFIA. And this is the image of the galaxy obtained with SOFIA, and we have a zoom in using 13CO image of this galaxy. It's NGC 1068, and we get a more detailed structure of magnetic field near the center of this galaxy. However, we are not making a technique which is only similar to polarimetry. We are making a technique which is stronger than polarimetry. This is, can be exemplified by measuring magnetization, local magnetization with gradients. Magnetization is characterized by alpha and Mach number, and low Mach number correspond to nearly parallel magnetic field lines, which high Mach number, alpha and Mach number correspond to disordered magnetic field lines. What we can do, we can make local, sub panels over our image, and over these sub panels, we can see the distribution of gradients, and the distribution of these gradients is giving us the information about magnetic magnetization. This is corresponding to simulations with different alpha and Mach number. This is not possible for polarization. You need to have bigger, much bigger areas of sky to find Mach number. But gradients are localized, and this is theoretical prediction in this small patches. The information about gradients. And as a result, for example, this is application of the technique to serpents. This is the distribution of alpha and Mach number within serpents. We also obtained with a different technique normal sonic Mach number distribution, and combining this is in a recent paper, in the technique which is different from Chandrasekhar Fermi technique, we are getting the distribution of magnetic fields over the molecular cloud serpent. This is, you see that it has a wide range of magnetic fields. With usual the Davis-Chandrasekhar Fermi, we get 100 microgauss, but here we have the whole distribution of magnetization. What I told you is a small piece of the gradient technique, namely the velocity gradient technique. There are other branches, synchrotron intensity gradients, synchrotron polarization, and others. So this is simply an illustration what synchrotron intensity gradients can do. This is an illustration using the synchrotron polarization from Planck and synchrotron intensity from Planck. Usually intensity is considered not able to find, to use to study magnetic field direction, but here we see a very good correspondence between the directions obtained with the synchrotron intensity gradient and synchrotron polarization. So the importance is that we don't need to correct for Faraday rotation. For Planck, it's not so important, but for most of other synchrotron polarization measurement is a problem. This is the application of our technique to X-ray and synchrotron intensity gradients. And this reveals, for instance, the magnetic field in Perseus cluster. We see magnetic fields which engulf a bubble in the cluster. We see them following the outflow arm and many other interesting effects which were suspected and were seen in numerical simulations. It's interesting that synchrotron intensity gradients reveal magnetic field, which is similar but not the same as the X-rays. And this is natural because these are different actually areas, volumes in the galaxy cluster that are being more important in synchrotron radiation or X-ray radiation. The differences are important and informative and should be studied. Well, in this talk, I could not surely talk about the most recent developments, and I was trying to convey you the major idea of the technique. But I just would like to advertise, and we can discuss with those interested parties privately today or any other day, that now we can use our technique to find this three-dimensional vector of magnetic field, not only the plane of sky distribution. We can also get the three-dimensional distribution of three-dimensional vectors using polarization gradients of synchrotron polarization. It is possible to use interferometers, and the great advantage for use of gradients with interferometers is that we do not need single dish. In fact, this is again a theoretical prediction of the concentration of information of gradients at small scales. We don't need the smooth distribution which is produced by interferometers. This is again a big advantage compared to polarimetry. Combining the polarization and gradients, we can use it in a very innovative way, synergetic way to get, again, images of galaxies with very high resolution without single dish. And also we developed recently the technique of separating velocity density contribution to position velocity space. And this goes beyond the application to gradients. And for example, we obtained a big power law or velocity fluctuations. In fact, we see how much related velocity fluctuations in molecular clouds and ambient gas. It's a really one power law. Well, this is my last slide, and I already told you that magnetic fields are important for many astrophysical and cosmological studies. At the same time, the new techniques are very important, and the advantage of the technique that I discussed today is that it employs rich data, even already archival data. Obtaining new data is very easy, and this technique is more informative to polarimetry and also synergetic to polarimetry and other ways of studying magnetic field. Thank you.
Great. Thank you so much, Alex. We have a few minutes. Let's see some questions from the audience. Please use the raise your hand feature, which is under the reactions button. And in the meantime, I'm curious. I come from a CMB background, so I'm definitely no expert in magnetic field modeling. But where do you see this going next in terms of informing studies of B-mode polarization and galactic foregrounds?
Well, we can produce very detailed maps of predicted polarization from the foreground. And we can, because of the new technique, we can take into account essentially everything and provide it the way that it's not possible using just measuring polarization at various wavelengths.
Okay, and do you see synergies with some of the planned ground-based or satellite missions? You know, CME stage.
We can use different information. We can use this H1 data. We can use also interferometric data, both H1 and synchrotron data, and produce the maps of foreground polarization with very high accuracy and very high resolution.
Okay. Thank you for that. Are there any questions from the audience? I see some of you have signed up for one-on-one meetings, so I expect there'll be questions then. And
yeah, looking forward to the meeting. That's really interesting, Alex. I think we're all just kind of sitting here thinking we need to go read your papers.
Well, I'm sorry, there are more than 30 papers on this subject.
Yeah, there's a lot in there, but this is amazing that you can do that. So yeah, thank you for your talk.
Okay, thank you.
all right, thank you all, and we will see you at next week's seminar. Have a great rest of your Monday.
Thank you, bye-bye.
Bye-bye.